So the interesting part of this talk is going to be when Roger tells you about the performance enhancements that he's actually put into version 14. But I'm going to delay his arrival a little bit, talking about sort of in general how we are approaching what I call primitive performance at the moment. So we have this goal of constantly, the goal as stated is to constantly improve the performance of the existing primitive functions and operators. And there are two main problems, of course. One, and the first one, deciding what to optimize, well, that's generally hard. Once you've decided what to optimize, we have, Dyalog currently has lots of clever people to make things run faster. But then the associated problem with that is as soon as you start working on improvements, there's a risk of slowing things down. And it's quite hard, in fact, even to understand whether that's happened. So first of all, deciding what to tune, well, a lot of that we rely on input from you. We've provided a couple of tools over the last few years. One of them is Applemon, which profiles the APL interpreter. So you turn Applemon on and you run your application, and then you get a log file which contains information like this. So it says, left arrow was used 59 times and was responsible for 21.5% of the CPU. Row was used 37 different cases of row, 65,000 occurrences, and then you can drill down on one of those and say, well, let's take a look at how comma was used, and you can get this breakdown that says, well, for the cases where the left argument was an 8-bit char, the right was an 8-bit char, the rank, left rank, right rank, and then the rough size of the arrays. There were this many occurrences of that, and here's the total amount of CPU that was spent doing that. So that allows us to get a feeling for how the interpreter is, sort of the profile of CPU consumption within the interpreter while it runs your application. And then the other view of the data is something you can get using quad profile and the new bracket profile user command, where you can get, there's a nice little graphical front end, at least if you're on Windows, that will break down the CPU consumption by the lines of your code so that you can see where the hotspots are. And if you think there's a mismatch between the use of a primitive function and how much CPU it's consuming, you can call us and say, if you could optimize this case, it would speed our application up by some amount, and then we have a meeting and get to work on it. So please do send us your code. Please use Applemon on your applications. If you have standard benchmarks that you have in your application to check whether performance is okay, try running it every now and again with Applemon and send us the log files or look at them yourself if you're not comfortable with sending us the files. Now, of course, as you add Unicode and 64-bit and more object orientation and better error messages, or even sometimes just as a side effect of tuning one thing, you'll have other things slow down. And the thing I really want to talk to you about is something we've built internally called the Performance Quality Assurance Framework, which is an internal tool that we use to measure the performance of individual, or to try and measure the performance of individual primitives eventually on a daily basis. So the goals that we have set for ourselves is we want to reliably detect slowdowns of 2%. So anything greater than 2% is the goal. If any particular case of the use of a primitive slows down 2%, we want to know about it. And we haven't done this yet because I'm still working on the reporting, and I'll show you why that's taking time in a moment. To publish a performance certificate with each version of Dyalog APL, which shows which things have speeded up, which things have slowed down. And then ideally, we also want to get to the point where maybe every night this thing runs, every time the system is built, we get a little report telling us whether the latest check-ins slowed things down or speeded them up. This is quite challenging because there's a huge number of different cases to test. And what we found when we started doing any measurements, that getting repeatable timings, reproducible numbers, is almost impossible. When you're timing, how long it takes to do scalar 0 plus scalar 0, the amount of CPU consumed by the function you call to ask what time it is in the operating system has takes more time and has much greater variability than the time it takes to do this actual operation. Or some of the operations, it's comparable anyway. So APL, of course, is a good tool for generating test cases, and Roger did the hard work here, and he actually generates, I think, 14,000 different cases with 600 different variables that are used. And we then go through, in order to avoid interference with other parts of the operating system doing stuff and so on, we'll repeat each expression for a total of 3 or 4 seconds, split up over time, 10 different runs of about half a second each, and then collect the data and go back again. So here's 100 of these 14,000 expressions selected at random, and there's 13,900 others that you'll have to imagine. So you can see there's some variable and a primitive and some other variable, and then sometimes there'll be operator expressions and so on and so forth. We try to create everything you could imagine. And then there's these 600 variables which have names which encode what the data type is of the variable, something about its size, so we generate arrays of varying sizes from 1-element vectors, singletons, up to 10K vectors. Sometimes there's a special letter added to say what the domain is, because we know there are switch points in the primitive function, so we can see whether it's non-zero or positive, and so on and so forth. We also create tall arrays and wide arrays and so on in the various sizes, and then we call all the primitives with these different cases. And we have a dedicated machine that we use for this. It has to be a real machine, not a virtual machine. There's nothing installed on it except APL. You run all the processes at high or real-time priority to avoid the interference with everything else. You pre-expand the workspace using 2000 IBeam. If you haven't looked that up, look it up to avoid dynamic workspace changes in size which might impact this. And then you write a very clever, you try and do the timing, so here's plus B0, and then we put a little left in, and we put lots of them in, and then every now and again we call this special IBeam, which calls the query performance counter. So we're trying to create enough work to time it without getting too much interference from the cost of the system clock. So this then generates thousands and thousands of timings for each call to this primitive. And we also, we adjust the number of times we call an expression so that we use roughly the same amount of time on each expression. Whether it's a big expensive expression, we'll only call it a few times. If it's a very small one, we'll call it very many times in order to get some data that's more statistically relevant. But even when you've gone to all those steps, you end up getting data which is very, very difficult to explain. So here's data collected from one interpreter on the left. There's the time taken to do, in this case, reverse on the first dimension DT2. And this is actually, I think, a comparison between two runs on the same interpreter, rather than a comparison between two different interpreters. And we still get these inexplicable shifts. And also just deciding what the data means, you can just average it, or we have algorithms actually that try and detect if there's what we thought was reliable, that if there's a very noticeable first peak, then we think that's a reliable indication of what the best possible case without operating system interference and so on, and that therefore is a reliable measure of the fundamental characteristics of this primitive call. And then, of course, having run 14,000 tests, you want to decide, well, what is actually worth going to take a look at? What should the developers now have a look at and see what they should improve? And the hardest part, this took me several weeks of trying to write different bits of code to analyze, was to get this chart. This is a comparison between two runs of the same version. And we divide the expressions up into groups, and we can see here that there are no cases of any group being more than 2% out when you compare a group of expressions between two runs on the same interpreter. So that's sort of, this is the baseline test that the tool is just working roughly. But even so, in two comparisons with the same interpreter, you'll find for certain expressions you can have quite large variations. And if you look in more detail, here are some charts that show, here are some expressions, and then graphically showing how many occurrences there were of that amount of time to run the expression. So we've got the one interpreter on the one side and the other interpreter on the other side. You're not sort of getting normal distributions. You're getting things that are obvious, a whole bunch of different distributions, which are dependent on cache, hit, miss events, whether the operating system decided to do something in the middle of it, and where you would expect to have one nice big normal distribution that you could just do some nice statistics on. You don't get that. You get these very weird distributions. So sometimes you get quite nice things, and you have confidence in them. But so the important thing to do is to sort of, based on all this data, produce a report. The developers then, there will be some false positives. They have to go and look at these charts and run their own tests. But the really important thing to do is to catch anything that actually slowed down by more than 2% and not generate a large number of false positives, because a false positive can be a developer's day wasted trying to investigate a slowdown. Right, so here's a more interesting report. This is a comparison, I think, from early this year, where for the first time, we ran the test on the new version 14 and the latest, or an earlier version, 13.2. And you can see that there's a whole bunch of, this shows that version 14.2 had some things that were very significantly better, but then you have a tail that doesn't look that good. And when you look at the details here, we can see, actually, this is not so surprising, because at the top here, the things that are doing best, so max scan on the first dimension, these are things that we knew we had done work on to really speed up. So the fact that they show up as things that really significantly speeded up is a good thing. But then at the bottom end, when you look at the worst expressions, what we see here, and this is really very discouraging when you see this, is these are a bunch of tests that have been added that don't actually test the performance of individual primitives, but they're testing things like control structures, loop going around in a loop, and you also see very, very trivial expressions like this is actually plus B0. That's doing the identity function on a Boolean scalar. Right? That's about the cheapest thing you could possibly get, and rho some scalar, and so on. So what we were seeing here was an increase in the interpretative overhead, we think mostly due to the function trains at the time, the work that had been done on the parser and the execution engine to add new functionality. So this, I think, is actually something we'll quite typically see when we go to each releases. We'll see some of these guys have slowed down a bit, and then we'll have specific cases that have speeded up. So yeah, like this one here, diamond, which I just think puts a bunch of diamonds in and executes it. But this was early this year, and I'm happy to say that this is what I ran this chart yesterday, I think, or the day before. So this is roughly the same comparison. It's a slightly newer version of 13.2. The other one was 16,600 or something, which I think actually makes the report more favorable, because there's likely to be more enhanced performance improvements that have been applied to this version of 13.2. And we can see that the tsunami is heading in the right direction, right? This bit has got wider and higher, and this tail has got smaller. And we still have 3 months to go. And one of the important things that we'll be doing in the last months up to the code freeze is looking carefully at the stuff that's down here and trying to make sure that we hit the 2% line. Whether we'll succeed in that, I don't know. But you do win some and lose some. Sometimes you can't do performance enhancements without slowing some things down. And it's the average. I mean, it's your benchmarks at the end of the day that matter. It's actual application benchmarks rather than whether a line full of diamonds with nothing else on it has slowed down. That doesn't necessarily mean anything to your application. So we haven't actually issued the 13.2 report yet because of the difficulty in simply producing a report that we feel confident about, but I think we're pretty much there now. And then an important thing, this is sort of very internal view of this project, is we want to hook it up to a My server internally so that anytime an interpreter's checked some code in, he can go in and say, well, there's this new build, please run the PQA tests on this and produce a report for me. And at the moment, we have the problem that the full collection of data actually takes about 13 hours, which means that it's not one of... well, Gianfranco hasn't done his talk on test-driven development yet, but I think what is the guideline? Unit test, the complete set of unit tests should run in less than a second to be useful? Yeah, okay, so we're not there with this. Right, and there's sort of a minor project, I don't know exactly when we'll do this, but I talked about Applemon before, and we have this goal where it would be really nice if we could bring the Applemon bound limits into line with what the variables that we create, so that we would be in a position where, based on one of these PQA reports, if you send us an Applemon log from your application, we could actually predict the performance impact that a new release of APL is going to have, because we could do a weighted average, weighted sum of the number of times you were using a primitive in a particular way with what the PQA data said about it. And of course, the holy grail is that every time there's an overnight check-in, the patch system won't actually build the DSS patch if the system didn't pass the PQA tests. Okay, so as I said, most of the real work was done by Roger. My job has really been staring at those numbers and trying to work with Adrian on Sharpplot to get some reports, graphs and things that would be useful. We still don't have this internally in production, but we're starting to really use it now to guide the final months of work on any release, looking at that red tail and making sure that it's as small as possible. So I'm going to hand over to Roger now to talk about some of the performance enhancements that he has actually been working on recently. But maybe there's a couple of questions while we switch that I could answer. Bob?
Thank you. Having been through most of this pit myself in the past, a couple of things you might consider are if you file the primitives, if you file the ones that use certain primitives under given suitable groupings, then that makes it easy for a developer to say, well, I've been messing with reductions. I'm going to run I'm just going to run the reduction test.
Yeah. This My server front end should have some way for the developer to limit also the number of tests.
And there's another thing you can do is to take, assuming you do it right, you can use the test scripts to provide you with code coverage of the interpreter itself.
Yes,
which helps a whole lot.
We are still working on a way of getting code coverage tests for the interpreter. We haven't quite managed to find a tool yet that really allows us to do that. Okay, so we take the rest of the questions after when Roger's done. Okay, thank you. Roger.
Thanks. Okay, so those are the topics I hope to cover in the remaining time. So version 14 has a number of performance improvements, and it goes off the screen. And in case you don't know, that symbol means infinity. There are three main underlying themes that bring a sense of order to these individual improvements. And the three themes are Visual Studio 2012, Boolean functions, and new constructs. Very recently, we started using Visual Studio 2012 to build the executable. And to my amazement, some primitives improved tremendously without any changes to the C source. So when that happens, it's a good thing because we didn't have to do any work other than having the wisdom to choose to use Visual Studio 2012. But I believe we can, for plus dot times at least, we can take some credit for it because plus dot times in Dyalog is not coded in the traditional way. It's coded in, well, the traditional way is row by column. And the non-traditional way, the current Dyalog way, is row at a time, what I call row at a time. It was done to be cache friendly, but it happens to make it possible for Visual Studio 2012 to speed it up by a factor of 2.5. And what happened there was that Visual Studio has a feature called auto vectorization, which uses the vector registers and vector instructions. And for matrix multiplication or plus dot times, it gets a factor of 2.5. The other feature in Visual Studio 2012, which we haven't explored yet, is called auto parallelization. The documentation describes it in terms of multiple threads, but I believe it's actually using multi-cores. So our job right now is to test and do benchmarks on the executable, not only to find things that are sped up without doing any work, but more importantly to verify that nothing important has slowed down too much. The second expression, not equals scan Boolean, is listed not because it's a particularly important function, but because we happen to notice that it became faster without any changes to the source. The next underlying theme in the speedups is Boolean functions. The initial impetus for this work started in, March 2012, when Morten was preparing to present the Game of Life at a software conference in Sweden. And as a result of that, we did some timings and identified areas that can be improved. And some improvements went into version 13.2, and these improvements are a continuation of that program. I'll focus on two of the improvements. The first two. The interpreter has a function, BMB, which is a bit mover, for moving a chunk of bits from one place to another. Typically when the bits are not aligned with a byte. Now this function, this bit mover, is used in a number of primitives. So by speeding up the bit mover, a whole bunch of primitives just got faster on Boolean arrays. There's a performance tip here that I can offer free of charge. Is that if you're working with Boolean arrays and it doesn't really matter that much how many columns there are, use a multiple of 8 columns. It's much easier for the interpreter to deal with. It's an inescapable fact of current machines that if bits are aligned with a byte, you get much better performance. Although we do try to give good performance when it's not a multiple of 8 columns. So if you have a Boolean array, no matter what the rank is, if you make the last dimension a multiple of 8, it's much better. The second Boolean function improvement that I want to focus on is b index of 0 and b index of 1, where b is a Boolean vector. This came about because in May of 2012, Arthur Whitney said on the K mailing list that the APL scans are not that useful, but b iota 0 and b iota 1 are much better. So whenever Arthur says something, I've learned that it pays to pay attention. So I did some timings and compared with J and found that J was actually faster than, on these two problems than Dyalog, which should not happen because J has byte Booleans and Dyalog has bit Booleans. So Dyalog should be 8 times faster, other things being equal. And from those benchmarks, I estimated that Dyalog APL on those two functions should be faster by a factor of 60. We actually achieve a factor of 780. And I think the bigger factor came about because I didn't take into account that if you have 64-bit machines, then that gives you the extra boost. Now, Arthur didn't explain the reasoning why he said, didn't explain why the Boolean scans are not useful, but the b iota 0 and b iota 1 are much better. But I think it must go something like this. Or scan b and b iota 1 contain the same information. But b iota 1 is just a single word, whereas or scan b takes the length of the vector to contain the same information. So it's much more efficient to do the index, even the result. And moreover, there are follow-on effects because you can either do b iota 1 drop of x or scan b / x. It gives the same answer, but the drop is much faster than the compress. It has to be because with the drop, you know that you're dropping off a chunk all at once. With the compress, you don't know where the ones are. And likewise for b iota 0 and scan b. So actually, b iota 0 and b iota 1 underlie several of the Boolean scans, and those scans are now faster as a result. Now I go on to new constructs. They are speed-ups in the sense that they give you a way of computing important and useful functions faster than what you can do before. Of course, it's not exactly the same construct as before because you don't have those new constructs before. The first one was already mentioned this morning a couple of times. The expression at the top of the slide is a 2-train, or in the top, it computes the first place where x is greater than or equal to y. And you can work out the algebra and, work out what a 2-train means and do the transformations and arrive at this point, which is ordinary APL, so it really does find the first place where x is greater than or equal to y. And where does the speed up come from? Well, if, as Morten said this morning, if the hit happens near the beginning, you win big, because you exit immediately. You don't have to go right to the end to find the index of where it first happened. But even if you have to go all the way to the end to find the hit, or if it's never greater than or equal to y and you fall off the end, you still win, because you save on the time and actually the space as well to generate a Boolean, and then look for the one in that Boolean. That factor of 1.3 is so small because we're actually fighting against ourselves here, because we speeded up BIO to 0 and BIO to 1. Otherwise, the factor would have been higher, even if you go to the end. In general, the pattern is iota composed with B, and a comparison where B can be 0 or 1, and the comparison can be any of the arithmetic comparisons. Now, having seen the pattern, we know a couple of bright ideas. One is to make idioms of the equivalent defunds, so that the people who prefer defunds can benefit from these speedups. Now, this is an argument for trains as a tool of thought, because those defunds could have been idiomized or have special code any time in the last 20 years, but nobody saw it. But as soon as we have trains, we realize that there are all these patterns that can be speeded up, sometimes by infinite factors. And the other bright idea, one of them anyway, is, wouldn't it be nice if you have a primitive to find the index of the last occurrence? And I have just a symbol for it, iota underbar. The next new construct is the two-train n/ greater than or equal to at the top of the slide. And it asks the question, are all elements of x greater than or equal to y? Okay? In general, the question can be, are any, as well as the are all, and also how many. So that would be for or/ and plus/. And the comparison can be any of the arithmetic functions. And if you prefer, you can use the equivalent 1 epsilon comparison or 0 epsilon comparison. For plus/, there's no infinite speedup because there's no early exit. You have to go right to the end to count how many. Okay, and the factor 1.4 is slow only because plus/ on Booleans already phenomenally fast before version 14 is faster again in version 14. After we saw this pattern, we realized that it's the same as the inner product. So we thought to check whether there's an early exit in that inner product. There wasn't. There is now. Again, yeah, the pattern is quite general. These points. Next construct is match with rank. And the problem is our corresponding rows of X and matrices X and Y the same. So I generated some random matrices, and it's faster than what you can do before. Before, the best way to solve this problem is n/x equal to y, which cannot possibly exit early because it has to do the x equal to y in its entirety and then do the n/, whereas the match has the possibility of exiting a row as soon as it found out that it's not matching. And where the infinite factor comes from is when you have long random rows and you find out quite early that it's not matching and exit very early. Next is a problem that we looked at this morning, but now I can provide some factors of speedups. And the problem is to count the number of occurrences of unique elements of a random integer vector, million elements long, integers between 0 and 1,000. Again, it's a problem that we encounter in a tuning project with a client in July. So solution A is the current best one using key. And as I pointed out this morning, when you preface the universe to the vector, it has two advantages. One is that the counts come out sorted at the end. And second is that it provides a zero count for elements of the universe that do not occur, which in this case is would be extremely low probability. Solution B explores what happens if you don't know the range of the vector. So you have to find the maximum first. And the factor also gives you an idea of just how fast key is compared to max/. C is a solution using modify index assignment. And the factor is low only because that expression has been sped up in version 14. D is the best you can do in current APL if you can assume that the vector is sorted. S is the sorted version of X. And E is replacing that forward difference with what's it called? Window reduction? Dyadic reduce? Yeah. And the fact that the time didn't change suggested that maybe dyadic minus/ can be sped up. F is what happens if you have to sort the vector. And G is what happens if you forget to use the sort idiom. And of course there's H, which is the shortest one, but you can't really use it because the performance, both in time and space, is abysmal. Maybe I should move it up to see. It's the outer product solution. Okay. As I said this morning, query 0 gives you, in version 14, gives you a uniform random number between 0 and 1. And so if you take the floor of 5 times such a random number, you should get the numbers between 0 and 5 uniformly distributed. And for this sample, they are. Here's a neat one. Hex F is a function from the dfunds workspace that gives you the hexadecimal representation of a floating point number. And in particular, the first 3 characters are the sign and the exponent. For our data, the sign is always the same. And the first line, the first expression shows that the exponent 3fe are the numbers between 0.5 and 1. So if I do the key on the first three columns of the hexadecimal representation of all these million numbers, starting down from one exponent to the next, the interval is reduced by half, so you expect the number of occurrences to be half from one to the next. And they do for this sample. So this is a list of operands which are currently supported by special code in these new constructs. What the new constructs key, rank, and train, the way they're implemented is that they each have a general function, a function for the general case, and special code for specific useful cases. Or I call them special code, but you can think of them as idioms. So they're really families of idioms. If you find a compelling example which you think should be faster, you should let us know. And the definition of compelling is factor of 2. That's it. Any questions? Okay. Jay.
Why are some of these in grey type?
Oh yes. Sorry. The grey ones are the ones that we plan to do but haven't done yet. So the black ones are already done. I like to promise to do things that I've already done. So that's why I put the ones in gray. Ray.
Roger, I've noticed that you've been using right fork in place of parentheses in some places. Does that parentheses change the timing more or less?
No, it's just neater. I use the right tag.
It doesn't affect timing.
It shouldn't. Yeah.
I'd like to suggest that you don't want to burn one of your few remaining characters, iota underbar, when that same capability will be available through Jay's stuff, effectively for free as an idiom.
Except I think it's important enough that it's a single token rather than however long it takes to express that. Okay, it's longer than 5 characters to express that index of last. I prefer that to be a single colon, single character, whether it's iota underbar or something else. We actually run out of time. Thank you very much.